finish up with 11.3. On Friday, we got through to before the sky was falling, we got through the geometric series, how to write out the nth rule for that.
Yeah.
But what we did not get to was writing out the sum of the finite geometric series. Now, you're welcome. Now, when we're dealing with the sums of these things, that's when we're taking and we're adding everything up. This also has a fairly simple formula to work with. When you're dealing with the sum of a geometric series, let me explain what it looks like. You have the sum of however many terms, that n value. Remember, sometimes they're asking for what's the sum of 16 terms in the sequence, what's the sum of 5, and so on. What we do is we take the first term in that sequence and we multiply it to some funky looking fraction. It's 1 minus the rate to whatever that nth term may be over 1 minus the rate. And so far today, you guys, you'll notice it looks like a really weird formula for something your calculator does for you. As long as you know how to type it in correctly, you're going to be just fine. So, once again, as we're looking at this, I don't think I have anything else here. It's just, for the lack of better terms, it's that sum of however many terms, that's what the n stands for. Bless you.
Thank you.
Whatever the first term was in the sequence, times 1 minus the rate to that term, so 1 minus the rate. So let's look at it. Here's a sequence. Excuse me. I have it on the wall right there too, okay? The sequence itself, they're telling you that it's geometric. So once you know that it is geometric, it's a matter of finding the rate. Do you remember the shortcut for finding the rate? Number 2 over number 1. Yep. So in this case, we have a geometric series of 1 plus 5 plus 25 plus 125 and so on. So the rate is 5. Everybody agree? Yes. All right. What's your first term? 1. So I write out my first term is 1. My rate is 5. I do want us to get in the habit of always writing out the nth rule for these. The nth rule, the generic rule for this, is also called the explicit rule. I always call it generic. I don't know why. So just to write out the nth rule here, remember your nth term is first term times the rate, the n minus 1. One of the reasons why I'm trying to get us in the habit of writing this out is tomorrow we're going to talk about what's called a recursive rule. And the recursive rules use this nth rule. And they're very easy to work with, interchanging with one another. As long as you know how to write out the rule, the recursive is like 2 steps and it's nothing. So this is easy. This is 1 times 5, the n minus 1. Everybody okay with that?
Yeah.
All right. Now we want to find the sum of 10 of them. So what's my value of n? 10. Since I want to find 10 of them, I'm going to find the sum of 10 of them, which means I start with the first term times the quantity 1 minus my rate to that n power over 1 minus my rate. And I know all of that stuff. I know my rate, I know my first term, and I know my n value. It's plug and chug. Never heard that?
No.
Seriously?
But the more you know.
New generation
So in your calculators, you can type this in exactly the way you see it, and you're going to get the right answer if you type it in the correct way. Do I need to put the 1 in my calculator? No. No. Do you guys remember how to create a fraction bar?
Yes.
How?
Alpha y equals.
Usually helps, yes. You know what movie was on, was it Saturday? I don't know why I started watching this. You guys ever see Star Trek 4?
Oh, Search Response?
It's the Voyage Home, the one with the back rails.
Is that the one where they have to save the whales?
Yes. So he sits down on the computer and he goes to go to the computer and they talk to their computers. And then they realize he's got to pick up the mouse. So he goes, hello, computer. And then he had to use the keyboard. I just thought it was funny. Anyway, so we go our fraction bar, and we type it in exactly the way you see it. 1 minus 5 to the, to the 10th over 1 minus 5, and hit enter. Big
Okay,
number.
that's what I got.
2, 4, 4, 1, 4, 6.
Is there a fraction option that gives you the power?
Oh, carry. Carry. Okay? I'm not trying to simplify 1 minus 5 and typing in -4. That's too much work for my poor little brain to work. I made up a word there, porny. It was poor little. I don't know. I typed in exactly the I tried to avoid just. Anyway, you get really big number. America. I give up. All right. All right. So what this just said was the sum of the first 10 numbers in the sequence is a really big number. Yes. 2 million and something. Okay. The second part is where I'm going to introduce you guys into something you've never done before. The second part. It is pretty I know. Find end. What this part is asking you to find out is how many numbers that in the sequence would you have to add up together to get 3,906. That's what this means. So we're trying to figure out the value of n that tells you how many you have to add up. Remember, numbers in this sequence is just this: 1, 2, 3, 4, 5, 6. How many of them would you add together? So here we start out with the formula. The sum of however many is your first term, 1 minus the rate to the n over 1 minus the rate. We know the first term and we know the rate. Do you agree?
Yes.
Yep. We also know the sum of however many has to equal. So you substitute in. We're solving now for n. 3906 will equal my first term times 1 minus 5 to the n over 1 minus 5. And this is where an algebra problem comes into play that you guys have never solved before. Where's n? It's an exponent, and you've never done that before. It's very easy to use. So, does everybody agree that I don't care about the one outside the parentheses?
Yes.
Does everybody else also agree that the 1 minus 5 is -4?
Yep.
Yes, sir.
How do you undo dividing by -4?
Multiply by 5.
Can I multiply both sides by -4?
Yes.
Yep. All right.
Yeah.
So 4 to
So that's negative 15,000.
is it 524 or is it 15,624?
15,624.
I always mix that up. Thank you.
Cat.
Equals 1 minus 5 to the nth power. Are we okay so far?
Yeah.
Yes.
If I want that -5, or see how it says 1 minus 5 to the n? If I want to make that a positive, what would I do to that -5 to the n?
Add it to the other side.
Then what am I going to do with that -15 and change?
Add it to the other side.
What I'm doing here is I'm flipping these two values around. I'm going to add this here, and I'm going to add that there.
Would there still be a negative?
No, because is the negative in front of the one or behind it?
No, I was just saying from you multiply both sides by -4. Top side positive.
No.
They're both going to become positive.
If I'm multiplying this by -4, if I multiply it by, what you're saying, if I'm multiplying top and bottom by -4, it means I'm multiplying it by +1. I added the 5n and I added the 15, 6, 24.
Oh, because it gives us 625, gotcha.
Okay? Now, this is where something new is going to happen. Let me put this in terms of something that's a little easier to look at. What's 2 squared?
4.
Okay. What's 2 cubed?
8.
2 to what power is 6?
2/3.
2.5.
Do we know?
No.
No.
X
Here's
power.
where you have to do something to solve when you have variables as exponents. And to undo them, you use what's called a logarithm. You log it.
Oh.
Now,
I heard you said
you use these in chemistry. You use logarithms in chemistry. You usually just hit the button, but what logarithms allow you to do is they allow you to change bases. Does anybody know what a base is?
Yes.
What is it?
It's that giant
That giant number. Which giant number?
5.
Good.
You can't do
This
that.
is a base, and this is the exponent. You agree?
Yes.
I used that button.
Well, good. Now, in order to be able to, undo this exponent, if you will, I have to use a log that has the same base as 5. So what would be the same base as 5? Log base of 5. Here's what happens. If I take the log with a base 5, that undoes the exponent. It allows the exponent to drop.
And then they switch.
Now, this is a very simple thing to think of to do here. This log base 5 of 5 equals 1. Once again, a logarithm is how you work with exponents. It's a relationship between a base and its exponent. This is going under the assumption that we've already taught you guys chapter in this book, and you remembered how to work with exponents. Just the fact that you haven't had chapter, I'm showing you a one-step process to do this. So when we go back to chapter, you'll remember. What happens here is that this is an undoing process, Mr. Gonzalez. To undo something, you use that same base. So if I log base 5 on one side, what do I have to do to the other side to make it happen?
Log base
Base
5.
5.
I got that.
Now, in your calculator, there's a button.
Where's log? Is it by tree?
Is it in math?
That was different.
Hey, Mr. Gonzalez, remember about logs?
Yeah.
What about them?
Those are the things that lumberjacks work with.
Oh, here it is.
No, the things are heavy
He
to
can make it
work.
work.
Yeah, big heavy wood, yeah.
He can make it work when I can't.
It's better than that, it's good.
No.
Wait, what?
Come on, you remember that, right?
Ren
Math.
and Stimpy, Ren and Stimpy.
Oops, wrong one. Alpha window.
It's already out.
Were you guys going Ren and Stimpy?
It's a different log.
Yeah, that's a log. Which is a log.
There's,
But it says the exact same thing.
well, there is a different ones. There's a different ways to get it. I'm just showing a quick way of getting to it.
Well, the red one.
Ladies and gentlemen, there's a log button on your calculator. The button that says log right in front of you on your calculator, underneath the x squared, that's a base 10 log. We can change the base of logs in order to change what the base is. Here I'm going to change it to log base 5. So I hit alpha window and I go to number 5 and it comes up with this screen. The cursor is flashing at the subscript for log. What do you think I'm going to put there? What am I going to put in parentheses?
5. Giant
No,
number.
it's
15. It's 6. 25. Why?
That means 5 to the 6th power equals that big old number. 15, 6, 25.
That's weird.
It is.
Hey, before they had calculators, did they teach this?
Yes, you
So
gotta
you
use
have to figure it out.
tables.
Right.
It's not bad. It's just there was literally the books of numbers that you had to look into. And once you learn how to do the index, it's very easy to do. So the answer here,
So we'll never learn. I like that.
how many would I have to add together to get 3906?
6 of them.
That's what that means.
Oh, alright.
That, don't you mean multiply?
No, what is the, I'm trying to figure out what is the sum, what is that sum going to equal 3906? How many of these would I add together? I'd have to add 6 of them together to get to that value. That's what that means. Okay? Now, once again, this logarithm,
Yeah, if you look at it, you can say I know it.
this log stuff,
Yeah, it's.
this value is always going to be whatever this is. Whatever that base is. That's what you change it to in your calculator.
All right, it's down.
Okay? That log base b is how you change the stuff around. We do a whole lot of stuff with logarithms and exponents later on in the school year. They're really not that difficult to work with. There are a lot of properties and stuff involved with them, but I think with doing this stuff, it's a one-step process to be able to figure out one other algebra problem. So now you know how to do another algebra step.
Yay.
Yay! So, oop, thought I had it open. Try this one.
Which one?
2 parts again. I'd like to figure out what is the sum. What's the sum of 14 of these in this sequence? Or excuse me, in this series? Just like we did our first part there. Remember, we got a really big number. And then the second part is, how many of them in this series would I have to add together to make it equal to 341? It takes a second to figure it out. Let's just.
Are equals 4, know that.
I messed up on my notes, so I gotta stick
For part A, are they asking us to define what 14 number was?
No, you're trying to find the sum of 14 of them. What was that? When I move that negative, how do you move a negative? Add it.
Why do you still have that one there?
What's that?
Why do you still have that one there? Can't you just like cancel that out since you know the first term is 1?
You can if you want.
Okay.
If you feel like it.
And when you start typing in the calculator,
Oh man. These are fun. Got the answer.
so you walk through it. It's a really big number.
Really big.
I don't know. I don't know what else to tell you. And then, and remember, you don't have to put in the parentheses with the 1.
Yeah.
There you go.
89.
Oh, I forgot I had to do that on everything.
Did you write it as -3?
No, I did.
Yeah, well.
4 to the 14th, and then I made it -1.
Don't do that,
I forgot to do it.
guys. Remember, when you get to this part here, since you're just using direct substitution, don't overthink it. Just all you have to do is type it straight in. You're gonna get the answer right every time, hopefully.
8,
Alright.
9, 4, 7, something.
Yes, that's what I said. Really big number.
Really big number.
Are we allowed to do that?
No, I would suggest really big number not being the correct answer on a test,
Oh,
though.
I was gonna say, I'm gonna test it. Could we do really big numbers?
Just write a really big number for everything.
You're welcome.
I got you.
Second part. Second part again, we have to set it up so that way we find how many of them we have to add together to equal how much? 341. So we know that the sum of however many is going to equal 341. We're still using that we have our first term was 1 and our rate was 4. So we substitute in. 341 will be first term 1 minus 4 to the nth over 1 minus 4. What am I going to multiply both sides by?
3.
Good. Multiply both sides by -3, you get, what is that, -1023, I think? And then can I simplify this on the right as just 1 minus 4 to the nth?
Yep.
All right. This is where I do the adding of to both of those negatives.
Then you plus 4.
Did Did you guys get 4 to the nth?
Yep.
1024?
Yep.
Oh, this
And then
is
log
like
base
24.
How do I undo this exponent?
Log base
Log base what?
4.
Log base 4. When you log base 4 of both sides, what did you guys get for n?
5. It's a lot of work just to get 5.
Yeah, it's a lot of work just to get 5. And granted, there's going to be times when you see it, you might be able to figure it out real quick with some of the patterns. This one isn't that bad because I think it gave us the first 4 terms in it, and you probably have figured it out. So when I told you guys we're going to do this logarithm stuff, did you freak out?
Yep, not really. Sure did.
I know. And like I said, by going out of sequence of some of these things, we're kind of intertwining some of the stuff that you might know or might not know. Okay? Was that all? Yeah. Yeah. Okay, 5. Yes. I don't even tell me. I didn't swear, so here we go.
Oh gosh, I'm really behind.
The answer's 5, right?
I know the answer is 5.
Yes, sir.
You know the
I told you.
No, I'm getting there step by step.
right there.
One is 4A.
No. So let's take this a step further.
Oh.
And you can't become yourself. We talked about summing of geometric. We've talked about summing arithmetic. These are both in terms of finite. There's an end. We're figuring out what this nth term is. We know that there's a stopping point, however many we had to get to. But what happens when we have to talk about infinite? Remember earlier this chapter, you guys were looking at a problem like this, where it was n equals 1 to infinity?
Yeah.
And you were trying to figure out how do you add up all of those? And I told you, just wait, I'll show you how to make that work. I'm going to show you that right now.
Oh,
This is
thank
part.
you.
This is that other part of this. Now, if I write this as 3 times 0.7 to the n, if I write it like this,
Where's the decimal coming from?
this is asking you for the sum of an infinite geometric series that has a first term equal to what? 3. And what's my rate? 0.7. So this mirrors the idea of a sub 1 times r to the n minus 1. Does everybody agree? All right. Well, in order to be able to find the sum of this infinite series like this, there's one rule that you have to follow. The value of r, the absolute value of r, because remember sometimes r is positive, sometimes r is negative, depending on what you're multiplying by, has to always, always, always be less than 1. Has to be less than 1. If it isn't, this won't work. This is how you find the sum of an infinite series, infinite geometric series. Can I get closer and closer and closer and closer and closer to her head without touching it? Yes. In theory, right? I'm approaching her forehead, but I'm not going to get there. Right? Why not? What's half of 2? What's half of that? Fractions. What's half of that? What's half of that? What's half of that? What's half of that? Are you getting smaller and smaller and smaller? Will you always be able to find a number smaller?
You never get to 0.
Correct. You approach it, but you never get there. So here's what happens. You get the following formula.
Oh, that's just mean. What's that symbol?
Absolute value of r is less than 1.
I'm not touching you. I'm not touching you.
I'm not touching you. Yep. Now, in this case here, I'm going to say that the sum, there's no subscript here, just the sum of an infinite geometric series is always the first term divided by, this is where it gets funky, 1 minus the rate.
I'm alone.
That's it.
And the rate has to
That's
be
how you
less
find
than
this.
1.
This is to find the sum of an infinite series where r, the absolute value, has to be less than 1. That's the only rule. If that R value happens to be 2, you can't do it.
Wait.
You can always be approaching something, because you can always add another fraction to something. So if you start thinking about, let me show you this. If you have a curve,
Is that what the bell curve's gonna be like for a grade?
Oh, whoa.
do you know what that dotted line is called?
The highest point.
The place you won't
The
hit.
dotted line.
The place you won't what?
Hit.
Place you won't hit. Place you won't hit is called a asymptote. It's an asymptote.
Arrest That's what you just said.
Asymptote.
That's not what you just said.
Yes, it is. Exactly what I just said. It's an asymptote because she was trying to figure out what it was called. So what's happening is if you take a geometric series and you keep adding terms to it, you're going to approach something. What are you approaching? Well, eventually you're approaching this value. So if we go back to that example I just threw up there with this, what my first term was what? 3. What's the rate? Okay, oops. Sorry, 1.7. So in order to figure out what the sum of this would wind up equaling is nothing more than 3 over 1 minus 0.7. I think it's 10. No. 3 divided by 0.3 is 10.
How do you?
It's nothing. What's that?
That's
not your approach.
Yeah, this is wizard.
But you continuously, as you get to it, at some of these approaches, it's an approach. What is it approaching? It's going to get to that value. Eventually, we'll get there.
It's going to get 10?
Eventually.
It will never get over 10.
It will never will.
Wait, I ever get to 10?
Because you can always get a number closer to it. I'm not touching you. I'm not touching you. I'm not touching you.
Does it ever hit it or no?
No.
Never.
I get you.
It's an approachment.
So
Okay.
whatever
Now-
you do, all plus infinity term, then you almost touch it. Never's your turn. We started with fish and then it goes down.
All right. Let me get another one here. It's
Me too. It goes on forever and ever and ever and ever and ever and ever. I don't know how you get it.
sorry. Let's do this.
Alright. 1 minus 1/4 plus 1/16.
I want to find the sum of this infinite geometric sequence.
Wait, did we on infinite?
This is the infinite ones, yeah. I'm going to tell you this is I want to find the sum of this infinite geometric sequence, which means the only things I have to figure out is, first of all, what my first term is and what's my rate.
1 is your first one.
Your rate.
My first term is 1, and my rate, what am I multiplying everything by?
Negative 1/4.
Negative 1/4. What is the absolute value of negative 1/4? Is that less than 1?
Yes. Yeah.
I take the second term divided by 1. Remember, I always take the second term divided by the first term? Okay? Everybody okay with that?
Yep.
So, to go find the sum now, the sum of this would equal first term over 1 minus the rate. You get 1 over 5/4, otherwise known as 4/5. If you added these things up continuously, it'll get to 4/5. 0.8 it might spit out your calculator.
Math just confuses me.
And if you notice, each one of those chunks, you're starting at 1, you're subtracting a quarter, but you're adding a little bit more, you're subtracting less, you're adding more, you're subtracting, you're
Like 3 steps forward, 1 step back.
yes, exactly.
Can I put that on the window?
Yeah, that's good.
That's a poem.
It's a song.
Yeah. Yeah, it's a little poem.
What song?
Wait, what?
Wait.
2 steps forward.
One other thing I wanted to,
-1. Yeah.
if you go in your calculator and type it in exactly the way it's shown, you'll get 4 fifths for an answer.
Alright, that's fine.
Now, one of the other things I wanted to show you really quick here is, if I'm looking at this generic formula here, do you guys see that there's 3 different variables? The sum, first term, and the rate.
Yeah.
So if you're given 2 of them, could you solve for the third?
Yes.
Okay, let me give you some homework.
Alright, no, you don't have to.
Why do you write things?
Come on.
Tomorrow, Tuesday?
I got to copy it in here. You can put all these things, 11-2 I'm not going to worry about collecting, but the 11-3 stuff, we'll put it all together with this and this. I have a couple of problems with 11-3 and 11-4 together.
Alright.
This one it loads, I forgot to copy it in.
Was that log reference?
These please. Alright. These please. These guys here, 11-3, I gave you one more of those problems where you had to do the system, where you're given the 2 of the geometric. Well, I gave you one more that has the system. These guys are the find the sum, using the sum values. Yeah, and then the 11.4 is using that infinite stuff. You'll find out that those shouldn't take you 4 minutes.
Wait, is this all
Should
organized?
Yeah. Yes, sir. Yeah, that's why I said just go ahead and add that onto your 11.3 stuff, and I'll get it all tomorrow.
Okay.
Okay? Should be pretty painless, I hope for. I hope so.
Do you want to see a cool drawing I made?
Oh, yes, you do. You want to see it. Wait, is this the bagel one?
Yeah.
Yeah.
It's a good drawing.
Come on, look at it.